Today we are going to a new subject, new topic. Small recap. So chapter 1 is a basic techniques for algorithm design. Actually, not only design but also analysis. So I show you. I showed three basic techniques. They are divide and conquer, and dynamic programming, and backtracking. Okay. Now, our new chapter is online algorithms. Okay. So until 2 weeks ago, what was our main goal? What was our main difficulties? So our main goal or difficulties. Let's say difficulties. This is not so good. Until 2 weeks ago, our difficulty is just computation time. Okay, so our goal is always try to develop, try to design faster, more efficient algorithms. So our main goal is computation. Our main difficulties is computation time. Now we change. Our goal is completely changed. Or well, not completely, but now our main goal is not computation time, but lack of information. That means we don't have complete information. We have only partial information, but we still design our algorithm that works for partial information. You already know. I already showed you a situation. Typical situation is stock investment. So company A okay. So this is the stock price of company A, and suppose that you have 1,000. You have 1,000. You are now holding 1,000 stocks of company A, and exactly this is today. You know, this curve is actually something like the real one. As you know, in Japan, our stock market is quite booming right now. So this exactly looks like the real stock prices. Okay, anyway. So suppose this is today. And suppose that you are holding 1,000 stocks of company A. The question is to buy more or to sell some. Okay? The question is you better sell something, some stocks, or you buy more stocks. That's the question. Of course, you don't know the change of prices from now on. Of course, so there is no complete solution. That is what I meant. That is what I mean. Lack of information. But still, you have to make a decision here. Okay? by using just the previous information. Of course, you can use the previous information, but you can't use the future information. But still, you have to decide. You have to make your decision about the current action. Okay? This is a typical situation. We do have some algorithms for stock investment, but well, that is a little bit complicated. So I'll show you more simpler examples. Okay. Today I'll show you 2 examples that is very interesting, and that is a kind of essence of online algorithms. Good. Example 1. Our first example. This is a little bit interesting. Okay. Beer restaurant. Just a beer pub. There are some near Hekumanben. Probably you love those kind of pubs. Okay. So the price is interesting. So beer will cost you 500 yen per glass. But if you pay 1,500, then free drink. That is 飲み放題. This is a very unique system in Japan, only in Japan. If you go to North America or Europe, it's very rare. Probably you never meet this kind of system, 飲み放題. Because if they do have 飲み放題, then that's Western people drink a lot, much more than Japanese. So the restaurant owner just go to bankruptcy. Okay, anyway, we do have this free drink system, 飲み放題. So your choice is which one is better for you, of course. So the question is, what is the best algorithm? What's the best algorithm? Of course, our goal is trivial. Our goal is to pay less. Of course, that's the minimum. With a minimal cost, you won't have much beer. Great. Okay, you might think this is trivial. If you want three glasses or more, then no. If you want more than 3 glasses, of course, 飲み放題 is better. If you think that if you 1 glass or 2 glasses are enough for you, then of course per glass, order per glass is better for you. So it seems trivial. Actually, it's not very trivial. Suppose that just think of this situation. Okay, now it's maybe Tuesday evening. So just go to some pub near Hekumanben with a friend. Okay, this is what you are thinking. Okay, tomorrow morning, I'm gonna have a class about from 8:45 about algorithms. That class is interesting, so I'm gonna get up early. That means, too much drink is bad. Okay, I have to control myself. I have to finish after 1 glass. Okay, so just you start drinking a glass. But the day is quite warm, so you are thirsty, and the beer is very good. You just finish 1 glass just in 15 minutes. I need more. Okay, 2 glasses might be okay. So you order another one, and just finish it, just in 15 minutes again. You are thirsty. Okay. After 2 glasses of beer, your brains somehow uncontrolled. Okay, you are the number 3, number 4, number 5. You cognized, I already had 6 glasses. That is one situation. That is one scenario. Okay, the other way around. Now this is maybe a Friday evening. Tomorrow is off. Okay, today I'm unlimited. Now you start. Of course, you paid 1,500, and you start drinking. Now you notice that you are almost finishing first glass. Then you got a call. Your cell phone is now your friends is saying that we are now 3 of us. We need a 4th guy. Do you understand? In Japan, that social life is very important, so you have to go. You have to go just after finishing 1 glass. You already paid 1,500, but you can only drink 1 glass. That is essence. That is the essence. That is the situation of online algorithms. You don't know the future. You don't know the future information. Okay? But still, you have to decide your action. That's very interesting. So, this is a formal description. Our problem is input. Input is a sequence of ones. Sequence of ones. But we don't know. How many ones? Okay. I do know input is a sequence of ones. Maybe 7 ones, 8 ones, 100 ones, but I don't know the number of ones. Okay. And when each one comes, for example, this one comes, okay, this is just you finished your previous glass. And this means you won. You want another glass. You want another beer. Okay, each one means you just finished the previous glass and you need another beer. Okay? Your action is, of course, glass. Order another glass or 飲み放題. Okay. Usually, in the reality, you decide, to order by glass or 飲み放題 at the beginning. But the restaurant would welcome you to change from a glass to 飲み放題 at any moment. Of course, by assuming that you would pay, you pay 1,500 for 飲み放題. The restaurant always welcome. You're changing from a glass to 飲み放題. So you can do that. And hours. Because this online hours have 2 requirements. Without any future knowledge. Any information, sorry. You have to decide your action without any information of future knowledge. And of course, this specifies definitely. No, this should be algorithm in a formal sense. That means you can write your program. You can write your program. That means it should not include something like, that's due to my feeling or something like that. So just, of course, algorithm is algorithm. You have to write some computer program. Okay. I'll show you three examples, three algorithms. Algorithm 1, this is always glass. Always glass. That means whenever you get input 1, you order glass. Okay, always order by glass. This satisfies two requirements without any information of future inputs, and action definite action. So satisfy two conditions, the requirements. Okay, no problem. Algorithm 2, is a 飲み放題. For the first one, at the beginning. Okay. So when the first one comes, you just order 飲み放題. Again, satisfies the requirements. That's okay. Algorithm 3, this is interesting. This is interesting. So this algorithm, due to this algorithm, you order glass until first two ones. And when the third one comes, you order 飲み放題. Okay? So this is glass. This is glass. This is 飲み放題. Then, after that, of course, once you order 飲み放題, then it's completely free. Okay? The third algorithm. Again, satisfies two requirements without any information of future inputs, and actions completely definite. No problem. Okay. Now the question is what? Of course, what's the best? Which one is the best? Of course, to discuss the quality of algorithm, we need to set up some evaluation system. We need some evaluation system. Okay, we use. Okay. We're going to use what we call competitive ratio for evaluating online algorithms. Competitive ratio. Okay, what is this? Competitive ratio of algorithm A is equal to the simple formula. Quite simple formula. I is input. Here, okay, I is input. So in this case, 1, 1, 1. So the I is input. A of I is equal to cost. Cost of algorithm A for input I. Of I is the cost of optimal offline for input I. What is optimal offline algorithm? That is the algorithm, the optimal algorithm that knows the whole input in advance. So this is something like God. Something like God. So suppose that you know the whole input in advance. For example, this time, you know that we're going to have 5 ones in advance. Then, of course, you can design optimal algorithm. That is what I call the optimal offline algorithm. Okay. And importantly, we consider the worst case. Worst case means this ratio is for algorithm A, the ratio the better it is better, the better this ratio is small. Okay. I'll show you. For example, in our case, in our current case, for example, sorry. This is opt cost. Opt 1 is of course 500 yen. Opt 11 is 1,000 yen, and opt 111 is 1,500. And opt 1111 is of course again 1,500, because just remember, opt I is the cost of optimal offline algorithms. That means we know the whole input in advance. Okay? This is kind of cheating. But we assume that this is this is something like God. So the God knows the future input also. So we compare the performance of our online algorithm A against the God, against the gods, the best possible algorithm. Okay? So in this case, twice 500, 1,000, 1,500, 1,500, 1,500. This is the optimal algorithm. Now, what about algorithm 1? Algorithm 1. A1 just remember that our first algorithm 1 is always ordered by class. So the cost is just increasing linearly. Okay? So algorithm 1, algorithm 2. Okay. So what is the competitive ratio? The worst case is for many ones. The worst case is for many ones. So if you have many ones, n ones, then the cost of offline algorithm is still 1,500, but the cost of algorithm 1 is 500 n. That means the competitive ratio, just diverges to infinity. In this sense, algorithm 1 is bad. Now you can see the ratio is well. Intuitively speaking, competitive ratio shows how well the algorithm plays against the God. The God knows the future input. So of course, the offline algorithm plays better than online algorithms, but we just compare the goodness of online algorithms against the goodness of offline algorithms. The best possible algorithms. Good. Now let's see the second one. What's the competitive ratio of the second algorithm? The cost of the second algorithm is always 1,500. Always 1,500. So what is the worst case? The worst case, of course, here. The worst case, the worst case is just the case that we have only one. That is the worst case. In that case, offline algorithm, the cost is only 500, but algorithm 2's cost is 1,500. That means competitive ratio is 3.0. 3.0. What's the cost of algorithm 3? Just remember, algorithm 3 it is up to 2 ones, up to the second 2 ones, 1 and 2 ones. You're gonna order by class. But at the third one, you change the order. Okay, that means this is the cost 100, 500, this is 1,000, and now that we already paid 1,000 and plus 1,500, so that is 2,500. After that, we don't, it's completely free. Okay? So, on competitive ratio, the competitive ratio is what is the worst case? The worst case is here. Worst case here. Maybe here. The same. Okay. This ratio is 1. Again 1. But 1.67. So this is the worst case. The competitive ratio 1.67. Okay? What's the best algorithm? So if you use this competitive ratio, we can say that algorithm 3 is the best among the 3 different algorithms. Actually, it's pretty easy. This algorithm 3 is optimal. You can never get better algorithms, strictly better algorithms. This is the best one. Clear? Okay? So this is the essence. This is the idea of online algorithms. Probably you might say that, wow, it's not realistic. It's a kind of a joke. Well, this might be a joke. But we have many problems, many online problems having the same flavor. The typical one is a ski rental program. Ski rental program. This is the typical example. We have many rental. Many similar programs. Again, input is 1. But I don't know how many ones in total. When each one comes, this is a time you want to go to ski. Okay, so maybe last December you want to go to ski. This January you want to go to ski. This February you want to go to ski. Okay, each one is a time you want to go to ski. And your choice is to rent a ski or to buy a set of ski. For renting a ski, maybe 10,000 a day, I don't know. Okay, when you buy a set of ski, maybe you have to pay something like 100,000 yen. Yeah, this is kind of a difficult decision, right? But this is a very, very kind of realistic, real problem. Yeah, many, many, many similar examples. Probably you can think of, you can come up with several similar problems, exactly the same flavor. That's the same flavor. So this is a very important online algorithms. Okay, now I'm going to the second example of today. Example 2. Oh, but I hope you don't have any questions so far. You understand the idea of online algorithms? The second result is a bit more complicated, So I hope you already understood the idea of online algorithms, basic idea of online algorithms. Okay? Good. The second result is linear research. This is a kana kanji. Transform. Typical example. Of course, the linear research can be used for many, many different programs, but the typical one is the kana kanji transform. So suppose that you are now trying to input some Japanese sentences into computer. Then, for example, if you type kanji and hit some key, maybe space key, then there comes this one. Okay? It seems like all students can read this. Okay, good. This is not, if this is what you wanted, then it's finished. It's done. But if it's not, you hit some key again, the next one comes. Next one might be, I don't know, this one. And again, you hit the space key, then it's a party organizer. This is I don't know. This is a difficult English name. This is auditor. I didn't know this English name, but I just look up the dictionary. Then this is auditor. But anyway, many candidates. Okay. This is a hit space key. Cost 1. Again, cost 1. Again, cost 1. Cost 1. Okay. That means if you wanted this word, then you hit the key 4 times. That is, what we think cost 4. Cost 4. So this is a cost. This is a cost. Okay. Interestingly, suppose that you selected this word. Then, after some time, you again type kanji, then hit the space key, then usually this guy comes first. Okay, this is what usually happens. if you select kanji, this one, then the next time it comes first. That is what usually happens. Okay, what is the mechanism of this? It's pretty easy, because now the system changes. System changes this linear list like this. This is just yes. Okay. Just changes the links a little bit. So now, this link, the first link goes to this kanji. Then it just goes back to here. And the previous, this link, it just skips. Okay? The system changes the links like this. This is a mechanism. Okay. So now I'll give you formal definition of this problem. Input is initial list. Initial list is of length n without loss of generality. Let's assume that the initial list 1 to n, 1 to 3 n. So this is 1, this is 2, this is 3, and this is 4. Okay? And the sequence of requests is, for example, in that case, the first request is 4. First request is 4, and maybe the second request is 5, third request is 1, and so on and so forth. Okay? The sequence of requests. And your action is just a search. You need to search item ij. So for example, if you get first request number 4, then you have to search. You have to search the linear list up to item 4. Okay? In that case, you need cost 4. Okay? But if the system changes the link structure like that, then if the second request is again 4, then your cost is 1. Okay? Our goal is of course minimize. Minimize the total cost. Okay. Okay, to make things easier, to make things simple, we concentrate, we restrict ourselves that we can use only this strategy. This strategy means moving So suppose that we can use only this strategy. That means we can move the accessed item forward. We move this item forward. Okay, that is what we can do that. That is only what we can do that. That is a sort of assumption. But this is quite reasonable. This is quite reasonable. Because it's changing this link structure is not so expensive. Because you already spent something like n step. Then the changing this link structure needs only how many steps? 1, 2, 3, only 3 steps. So if you already spent m steps, for example, then the changing this link structure needs another only 3 steps. So this is cheap. This is quite cheap. Okay. In this case, we move this guy to the exactly top. Exactly top. But you can move this guy as many positions as you like. Okay? For example, you can move this guy in the middle, something like middle, or maybe 2 positions. That is up to you. That is up to you. The question is, how many? This is a question. Our strategy is fixed. Our strategy is moving the access item forward. But how many positions? That is the question. Okay. As I said, there are many possible choices. To the top, by 2 positions, to the middle, there are many different possibilities. Ooh, what do you think? What do you think? For example, this seems to the top might be, this is what I said, this is what usually happens. But well, we don't have any future information. We don't have any future information. That means if you move this guy to the top, but you may never access this guy in the future. Then moving this guy to the top, it's not so good. Okay, you don't have any future information. Actually, in practice, when you are making some document, then if you use this guy, then the next time maybe you may use the same thing again. That might be in practice. But right now we have no information. We are assuming that you don't have any information in the future. Actually, we are considering the worst case. Consider the worst case. So if you move this guy to the top, then the worst case might be that you never access this guy again. So you don't know what is the best. What's the best? Okay? So now we are going to the competitive ratio. We are now going to the competitive ratio. Okay. it's not difficult to see this strategy by two position. This is not good. Why? This is our initial list and request. So always n. Always n. Request is always this guy. Always this guy. Then what is the cost? Our cost is equal to n, because it's the first n. We need to move 1, 2, 3, n. Okay? This is the first cost plus n minus 2 for this, because in the just we moved 2 positions. And if you have n requests, then it's something like n square. But optimal cost is what? Optimal cost is, of course, to move this guy to the front. At the beginning, it's the first input, first request. It means n plus 1 plus 1 plus. Right? The complete ratio is almost n. Of course, that diverges. Just go to the infinity. Means the complete ratio is infinity. That is not good. Okay. Now a theorem. This is awesome. So today's main goal is to prove this theorem. The real thing, starts from now. Maybe next 30 minutes. It's really important. We're going to prove this theorem. Move to front algorithm has a competitive ratio of 2.0. What is move to front? I'm sorry. This one. Always access the item to the top. A very simple algorithm. Okay? That algorithm has a competitive ratio of 2.0. Proof. Very clever. Why? Because we don't know what the optimal algorithm is. Okay, in the previous example, we do know optimal algorithm. It was quite easy. But this time, we don't know optimal algorithms. So even if we don't know optimal algorithms, what the optimal algorithms looks like, we don't know. But still, we can compute the competitive ratio of this move to front algorithm. That is at most 2.0. It's really clever. Okay, so let's start the proof. It's the beginning. Opt list. Okay. At the beginning, our list is just 1, 2, 3 through n. Just a linear list. And that is, we compare two different algorithms. We compare two different algorithms. Algorithm MFT, this is our algorithm, and algorithm opt. But at the beginning, two lists are completely the same, of course. Now, the algorithm, two algorithms are moving, then two lists are changing. Two lists are changing. Okay? So now, suppose that we are at step J. Step J. So we have opt. Opt list looks like this. And our algorithm lists look like this. Okay. Where's the red one? Okay. Now, step J, the request is item I. So request. Request item I, and the cost is I. Cost is I. And the cost for MTF is K. Suppose that the cost for opt is I, and cost for MTF is K. Okay. And what this means? What this means? Okay. This means the same item. Same item. Before I. Before I. It's again same items. After I. After I. Of course, this is a kind of a distributed. Just this figure only shows the number of items. Those items are completely distributed. But we have this many items before I, same items. This many same items before I, this many same items after I. And those items are different. These items are before I in opt, but after I in MTF. Again, those items are after I in opt, but are before I in MFT. So the initial list look like this, but step J, the list may look quite different. Two lists may look quite different. Do you understand this list means? Once again, this many same lists before I, that many same lists after I, and this portion is different. Before I, after I. After I, before I. Is it clear? Okay? Good. So, we suppose that this is a y minus xi, and this is not y, I'm sorry. K minus xi, this is yi, and this is xi. Oh, sorry, this is the order is bad. So assume that this size is y, this number of items yi, this number of items xi, then this is obviously, k minus xi is here. Okay, k minus xi is exactly this. Again, we assume that this number of items yi, this number of items xi, then this is, just a simple calculation. This size is k minus xi. Okay, once again, yi is the number of items which are before I in the opt list, but after I in the MFT list. Xi, number of items which are after I and before. Okay. Now, here comes the main point. Here comes the main point. Cost. What's the cost of move to front? MTF, MFT. I'm sorry, something different, something strange. Yes. Sorry. Move to front, MTF. What's the cost of MTF at step J? Of course, we assume it be K. Okay? We assume that the cost of MTF is K. Is K. But But we don't use that cost, that direct cost, but we consider the following amortized cost. Amortized cost. Amortized means just average. And it's a little bit different from average, but it's okay to think that this amortized means average in the following sense. Very important. Inverse J. Inverse J. It's an important notion. Okay, inverse J means inverse J is defined as the number of item pairs A, B such that the order is different in two lists. In two lists. That means like this. In the opt list, the order is A, then B. But in the MTF list, it's B, then A. This is what I mean. The order is different in the two lists. The number of such pairs is inverse J. Intuitively, okay. Intuitively speaking, that is the amount of difference between the two lists. It's quite convenient to think of this inverse J. Okay. So our idea of the amortized cost is when we lose, we get something. When we lose means large K. but small I if k is large. If k is large, that is the cost of our algorithm. But I is small. That is the cost of opt. So this is big, this is small, then we lose at that step. But we can get something. Okay? We get something. Something means this difference. The amount of difference between the two lists. That is why we say that this is average cost. Okay, I'll show you in a moment why this happens. Why this happens. I'll show you in a moment. Okay, now, from now on, this is just a calculation. In fact, T of j okay. Tj can be written like this. T of j can be written like this. This first k is, of course, this guy. The second one is the inverse j plus 1. Inverse j plus 1. And the third one is inverse j. Inverse j. Why this and this? Important thing is that we can count. When we count pairs, it is enough to count only this kind of pairs. Include I. This is the item which are now accessed. Okay, I'll explain. We are now, count a pair of elements, pair of items, like this and this. No, this pair, order of this pair is different. Okay? Order of this pair is different. But that pair is again different next step, right? Okay, this A and B. Here A and B. And here A and B. Order is different. But what moves? Only I moves. Other thing doesn't move. Only I moves. Then the next step, order of this AB is again AB, and order of this BA is again BA. Doesn't change, right? So that means, it is enough to count only pairs involving this I. That is enough. So, okay? So what is inverse j plus 1? This is step j, and step j plus 1, this guy comes the top. Then everything is after I. However, this I moves a little bit. Oh, I'm sorry. This alpha is a little bit. Maybe, I don't know. In the opt, in the optical algorithm, this guy also moved a little bit. Maybe, I don't know. Alpha may be any value. I don't know. Okay? But maybe a little bit move to the front, move to the top. Okay? Then the difference is what? The difference is k minus xi plus yi minus alpha. Okay? This value is here. Okay? This is the inverse, j plus 1. Because at the time j plus 1, this guy comes to the front, everything is after I. But these guys are before I in opt. So difference is exactly that value. At step j, of course, this is xi plus yi is a difference. Okay? So xi is before I, and xi is before after I, and yi is before I, and yi is after I. So the number of different pairs, okay, including I, is of course sum of this number and this number. Okay? Simple calculation. Just simple calculation. This value is exactly, 2k minus 2xi minus alpha. Can be bounded. This, by neglecting minus alpha, this can be bounded by this guy. And k minus xi is what? K minus xi. I'm sorry, k minus xi is k minus xi is at most I. K minus xi is at most I. Huh. Okay? Now you understand the meaning of amortized cost. Amortized cost. By doing this kind of compensation, the amortized cost is always twice the cost of opt. That's why I'm saying that when we lose, if we lose a lot, that means k is big and I is small, then you can get something here. So the amortized cost is still not that bad. Not that bad. At most twice the cost of opt. Okay, now after that, it's pretty easy. Just a simple calculation. Step 1, step 2, and step n. This is the cost of our algorithm, MTF, and this is inverse. Importantly, cancels. So we sum up all of them, then we can get this equation. It's pretty easy. And of course, this is 0. We are done. Just to change, just to change this formula like this, then inverse n plus 1 is positive. So we just neglect this. Then k1 plus km is up to t1 plus tn. But we already know that t1 is at most twice opt. t2 at most twice opt. And so on and so forth. That means this is at most 2 opt. What does that mean? That means our competitive ratio is at most 2. We are done. Or you can recognize that this proof is very clever. We don't know optimal algorithms. We don't know anything about optimal algorithms, but still we can calculate the competitive ratio of our algorithm, MTF. Wow. It's really clever. Yeah. So, yeah, this is I'll stop here for today's class. Next week, I'll show you a bit more examples of online algorithms. And also, probably I can explain that this competitive ratio 2 is optimal. So for this problem, for the linearist search problem, we don't have any algorithm whose competitive ratio is strictly less than 2. It's impossible to get less than 2. Okay? Probably I can show you that the lower bounds. Okay, so we are done for today, and see you next week.